All right. So any questions before we begin? Okay, if not, then right. So problem number 1 deals with this continuity and limits. So it's asking us to do something involving that. First, I'm going to refresh you guys on what we're supposed to know about continuity. So in the slides, you'll find this. And this is the precise, this is the definition of continuity. It's saying, so a function f is continuous at a number a if the limit as x goes to a of this function is the same thing as plugging a into the function. So if the values near a of the function are, if they're going to tend towards the same value as if you were to just take a and plug it into the function, then you have that as continuous. This is basically to avoid a point discontinuity. So I don't remember. Yeah, he sort of goes through discontinuities, but yeah, you kind of want to think of these as like the counter examples to this. So there's a point discontinuity, which would look something like this. You've got a hole in your graph, and then maybe you fill this hole like anywhere that doesn't lie on where it ought to be, and that would be a point discontinuity, and that would be a place where it's discontinuous. So to assert continuity, we really want that value, that hole, to be filled in exactly where we expect it to be filled in, and that's this equation is saying this. The little paragraph at the bottom is kind of spelling out that this one equation is actually saying 3 things at the same time. It's saying, first of all, that these 2 quantities on the sides, that they actually exist. So this 2-sided limit actually exists, which you can then unpack and say and know that actually means that the 2 one-sided limits have to agree. Right? That's what we need to say that the 2-sided limit exists. The second is that this function, that we can actually plug a into the function and we get some value out, meaning that it's not undefined at a. There's not this situation where we don't even have a definition for the point. I'm gonna put that back. I kind of prefer that. Okay, and then lastly, the equation itself. The 2 sides are equal. So this one equation is actually 3 statements in one go. All right, but how are we going to use continuity here? Well, the functions are continuous functions, so that's the first thing. And so really, we're essentially trying to shortcut taking the limit as being take the 2 sides and the 2-sided limits and seeing that they're equal. The shortcut is, if the function is continuous, if we can just say that it is by whatever means that we know how, then instead of taking a limit, we can just change the question into plugging in. Okay. So can we actually say it's continuous? Yes, we can, because cosine is a continuous function. This polynomial, x to the 4 plus 1, is continuous, and division of 2 functions is continuous. So we would start by saying, since cosine of theta over theta to the 4 minus plus 1, doesn't really, plus or minus is either is going to be true, is a continuous function. I'm going to abbreviate continuous. There's different ways to abbreviate it. Then this limit ends up equaling, you would probably want to recopy it, but I'm being a bit lazy. Cosine of pi over pi to the 4 plus 1. Okay, this is given to us by this equation. The limit is equal to that so long as the function is continuous technically at the number a, but in fact these functions are continuous everywhere, meaning on the entire real number line. Okay, and then next we just need to evaluate. So what is cosine of pi? So hopefully you think through the unit circle somehow, and you think that pi is, I don't know if I mirrored correctly, but yeah, what I do is I just rotate to pi, and then I think, oh, that's -1 for cosine. -1 over pi to the 4 plus 1. Okay, there we go. So we got that. Part B is very much the same thing. Since arctangent, I'm going to abbreviate it with atan. Atan of t times t plus 1 to the 4 is a continuous function. Some people also abbreviate function. Then we know that this limit is going to be equal to just plugging in. So it's equal to arctangent of 1 times this 1 plus 1 to the 4. Really, they could just say 2 to the 4. Okay. And well, I asked the other class this. What is arctangent of 1? Who can tell me? Yeah, this is the same. This is the same reaction I got. Okay, so that's really sad. Uh, arctangent. Okay, so the way you want to think about these arc trig functions, these inverse trig functions, they are the inverse function to the usual trig functions. So they're asking the reverse question. Okay, so inverse tangent of 1. Maybe I'll use the other notation also. Just perhaps that'll make you guys feel more comfortable. Tan inverse of 1 equals something. This is really asking another way of interpreting this is saying tangent of what angle is going to give you the value 1. It's the same question, just rephrased. Okay, and hopefully you can answer this question. What is tangent? What is question mark going to equal? Well, the first thing that comes to mind should be pi over 4. Tangent of pi over 4 equals 1. But you also kind of remember, oh, there's also on the other side of the unit circle, there's also a 3 pi over 4. And then there's also repetitions, right? Pi over 4 plus 2 pi plus any quantity of 2 pi. Well, that's not going to hold true for the inverse trig function. It's not going to hold true for the original function. And the reason is because when we define the inverse function, or these arc trig functions, what we do is we sort of do a cut of the whole number line. So maybe I do need to like at least draw a diagram just to show you guys. This is something you guys should know, but maybe you weren't paying attention. So tangent looks like this. It's got these little asymptotic things, and it cycles every pi, I think. But it keeps doing this, is what I'm trying to say. It keeps doing that. And your fundamental part, your fundamental piece is this one here. Starting from negative, I think, pi over 2 to pi over 2. Okay. Now, when you take an inverse function, what you do is you think of it as, at least the way I think about it, is you think about drawing the line y equals x, and you imagine reflecting the entire picture according to this line. So you reflect the whole thing. Well, the problem is if you reflect the entire tangent function, you're going to have something very, what is called multi-valued in mathematics. Let me, I'm going to go into this in detail, and I guess the other students will maybe end up seeing it. So the green one will become this guy, or sorry, the blue guy will become this green guy. But then you also have all these. I don't have a different color. I'll just use black. But then all the other ones are going to stack on top. They're going to be like those vertical asymptotes turn into horizontal asymptotes, and you end up having like this bunch of. You end up having this, and this no longer is a function, right? A function is supposed to be something where given one input, you get one output. You don't get like an infinite set of outputs. That's not allowed. So that's why when we define these inverse trig functions, inverse sine, inverse cosine, inverse tangent, all of them, we have to sort of take one of the fundamental parts of the trig function, and then we invert that, and we restrict the domain, and that like does some stuff. So what I'm trying to say is, in this equation here, you have an infinite set of answers. But in this equation here, you only have one answer, this pi over 4. And it's because of this process where we exclude all of the repetitions so that we actually have a well-defined function, inverse tangent. Okay, so that's a very long story, something that you're supposed to learn when you take trig, but may as well say it here. Okay, so arctan of 1 is supposed to be pi over 4. Okay, and then the rest of it, well, 2 to the 4th power, 16, and we get 4 pi. Okay. Questions so far? No? Okay. Part, or number 2. So we have this function. This is called a piecewise function, where we have these different branches. Where is it continuous? Where is it discontinuous? And in these places where it's discontinuous, is it continuous from the left or from the right? Okay. So hopefully you can see each of these individual functions are continuous, right? Then the only place where Q could be discontinuous is where we're sort of stitching together these functions. We're just sort of like arbitrarily cutting and joining them. So the discontinuity can arise only when we just sort of arbitrarily connect them together, and that's going to be at 0. So what we really need to do for this problem is we just need to test the limits, or the limit of this function at 0. So I'm going to write down the left limit, I'm going to write down the right limit. Not in that order. This is the right limit, this is the left one. Okay. Well, if we're only restricting ourselves to considering approaching from the right-hand side, then we actually are only talking about this branch. So I can simplify this limit, or the way that this limit looks, to just being about this continuous function inside of this piecewise function. Okay. And let me just go ahead and compute this. So I can now, since this is continuous, I can use the logic in problem 1 to say like, oh, we can just plug in. Okay, so cosine of 0 is 1. And so we have square root of 9, which is 3. Okay. For the second branch, or well, the other side of the limit, we are dealing with going to 0 from the left-hand side. So we're always less than 0. That's going to restrict to this branch. And so we can just simplify the limit as being this, and we can just compute this. So e to the 0 is 1. I just want to emphasize, because I see people write e to the 0 all the time, instead of just writing 1. Okay, now, there is a slide for this, but I don't know if I really want to copy or paste that. Me as well. So continuous from the left and continuous from the right. I think this this definition is a little bit, I'm not sure if I've ever come across it before teaching under Craig Spencer. But so what it's saying is like if the decided limit is equal to plugging in, and the other piece is just sort of floating somewhere. So if the decided limit, the left limit here is equal, then it's continuous from the left. If the decided limit approaching from the right is equal, then it's laptop is gonna die. Sorry. Yeah, if the sided limit from the right is equal, then it's continuous from the right. And if the two-sided limit is equal, then it's just plainly continuous. So that's why these definitions make some sense. Here we can see that if we were to just plug in, right, q of 0, we end up hitting this branch. We end up hitting 3. And so you see that this is equal to the right limit. So this lets us conclude that q of x is continuous from the left. Is right continuous? Wait, right continuous? Yeah, right continuous. Right. At x equals 0. And you can specifically say, since limit x approaches 0 plus q of x is equal to q of 0. This is the definition for being right continuous at 0. To answer the other question, where is q continuous? It's continuous everywhere except 0. So use a different color for that. Except x equals 0. Right. In the offset, you could have just immediately by looking at the problem, you would be able to conclude that it's potentially, or it is continuous everywhere except potentially at x equals 0. X equals 0 is the only place where there could be a problem. And if the piecewise functions were stitched together in such a way where they perfectly matched, then you could even say that it is continuous also at 0. It's just that we had to test at 0 to see like what is the behavior there. All right. Any questions on this problem? I want to make sure we go all the way to number 7. That's where we ended with the other class. So next problem we have is involving squeeze theorem. Let me find the statement for squeeze theorem. The slides are a bit out of order. Okay. So I have to copy two things. Just a second. No, I don't like that. Okay. Right. So this is what squeeze theorem says. So it looks like a very mathematically precise statement. Let's see. The thing that we're trying to do with squeeze theorem is we're trying to evaluate the limit of this function g. We're trying to take the limit as x approaches a of the function g, and we want to like somehow say it's equal to some number L. But for whatever reason, we don't know right away what the limit of g is. Okay, and the idea of squeeze theorem is if we can find an upper function and a lower function, if we can somehow see that g is sandwiched between these two functions, and if these two functions are simple enough that when we take the limit of the two functions, we can imagine we can actually take the limit of f and we can actually take the limit of h, and that they give you the same value, they give you some value L, these two facts combined will squeeze g so that it must take the value L. It must take the same exact value. And this picture describes it. So in this picture, the blue squiggly function, that's your function g. And it's bounded by this upper function in red and this lower function in purple. Right. But very easily you can see that this upper and lower function, if you take the limit as x goes to 0 in this case, the overall limit, the L value, or the value for L is going to be 0. And then that lets you conclude that the function in blue is also going to be 0. Although, like, you wouldn't necessarily, I mean, it's immediately obvious from the picture, but it's not immediately obvious from the function definition. See, it gives you the function here, x times cosine of 1 over x. That is the thing that you're trying to deal with, like, symbolically. Pretend that you couldn't draw it. Squeeze theorem lets us figure out these limits without actually plotting them using a computer. Okay, and now let's go over to here. So hopefully you see that there's some structural similarity between this problem and what's graphed. What's graphed here is you got x, and you got a cosine of 1 over x. Here we have a x to the fourth, essentially, and a cosine of 1 over x, essentially. So what usually happens with squeeze theorem problems is you're dealing with a sine or a cosine, and the inside is a 1 over x of some sort. The reason for the 1 over x is because that makes it oscillate infinitely fast as x goes to 0. Just like in this picture. See, the frequency gets infinitely fast as you go towards 0. And that's just to prevent like being able to directly plug in. The outer function is really what sort of what kills the infinite oscillation and lets you actually take the limit. And the statement that lets us use squeeze theorem for these types of problems in the first place is a property about the cosine and the sine functions. So cosine and sine, what you need to realize is that they're always bounded by the functions 1 and -1, right? If you think about the graph of a sine or a cosine function, they always do this kind of thing. They always oscillate, but they're always bounded between 1 and -1. They never I mean they hit it exactly. So in this picture it's a little bit off, but they hit 1 and -1 infinitely often, but they never exceed, right? And so what we can do is we can set up an inequality, a triple inequality is what it's called. So the inequality in this problem is going to be -1 is less than or equal to cosine of 3 over theta is less than or equal to 1. So we know this is true just because we know stuff about the cosine function. And then what we do is we multiply all three sides of this triple inequality by the theta to the 4. And that's going to bring us towards the statement we are actually trying to work with. Okay. And you can check like, okay, because theta to the 4th is always positive, you don't have any swapping that happens with these inequalities, right? Normally, like you kind of need to think if you're multiplying an inequality by a number, if the number is negative, then that flips the order of the inequality. Here, theta to the 4th is always positive, so we don't need to worry about that. Okay. Now the next thing about, squeeze theorem is that we need to take the limits of the bounding functions, the functions on either side. Okay. So what I'm going to do is I'm going to present this diagrammatically using these arrows. So these arrows represent that we're taking the limit, the same limit that this problem is asking for. Okay, so limit as theta goes to 0. You take this limit as theta goes to 0. We take this limit as theta goes to 0. And what does this guy approach? Well, it approaches the value 0. And what about this guy? Also the value 0. And what about this inequality then? So it's guaranteeing like this inequality is saying that this inner function is always between these two functions. And so what happens with this limit? Well, if it's always between 0 and 0, well, it's got to be 0. Okay, and that's the essence of squeeze theorem. So this is a pictorial way of saying like that we found this limit must equal 0, but this is not how you would present your work like in words or like if you were to write out your work. This is sort of like the scratch work, but if you were to sort of write out your work to be presentable, you want to say this as one line of work, this as another line of work, and then you say like by squeeze theorem. So you can see an example of that in the slides. I'm also going to do that. I'm going to do it in written form for part B, so you can see like what this is more supposed to look like. So this problem, part B, is somewhat similar to part A. It's just that instead it gives you with the bounding functions, and it tells you nothing, absolutely nothing about the function w, except for the fact that it is bounded by these two functions. And it's odd, but it does also make sense that this is enough. So long as like these two limits will squeeze down to a single value, you can figure out what the limit of w is going to be just by squeeze theorem. Okay, so just like before, we need to take the limits of these bounding functions. Limit as x goes to 5 of x squared. Well, that's just going to be 25. Make that look like a 5. And then also limit as x goes to 5 of 10x minus 25. That's going to be 50 minus 25, which is also 25. And these two values coincide. They're the same number. Okay, so then by squeeze theorem, we're able to conclude that the limit as x goes to 5 of w of x is also going to equal 25. Right? Because w of x is always between these two functions, And as x goes to 5, they both approach 25. That sandwiches the possible values that w can take on. And we end up getting 25. And so that's it for this problem. All right. Any questions? I feel like I'm going a little bit too slowly. I'm going to have to speed up a little bit. Okay. So for 4a and b, there's these special things called trig limits. And in the slides, Craig Spencer, he splits them apart and doesn't really like put them in one boxed thing, just like with these theorems. Like that, it would have looked a bit nicer if he did that, but I'll just write them off to the side. So there are these special limits called trig limits that you are kind of supposed to have memorized. So the first one, limit as x goes to 0 of sine of x over x. This takes the value 1. And the other guy, limit as x goes to 0, 1 minus cosine of x over x. This takes the value 0. Okay. And these are necessary to do this problem. So you have to know these to be able to make any progress with this problem. Okay. So you can see right away, like this has a sine of theta over theta, except it's reciprocated. So and also we're supposed to use limit laws, so we're supposed to like step through this kind of slowly. The first thing we do is a limit law. Actually, we pull the 2/5 out. So there's a limit law that says we can do that. Made it look kind of bad, but okay. The next thing is, well, this doesn't precisely match sine of x over x. This is the reciprocal of that. How do we make it actually match? Well, what you should realize is this is the reciprocal. The reciprocal is raising to the negative first power. And so we can actually write this as sine of theta over theta raised to the negative first power. And there is a trig law that says the limit of something raised to a power is the same as I think I flipped it around, but something raised to a power, then take the limit is the same as something take the limit raised to a power. I'm just going to write it. We can push the limit inside of the exponentiation, or the power function. It's always confusing. Like how do you distinguish between exponentiation and raising to a power? All right. So this is the limit law. And then this guy is 1. We can reciprocate 1, and we just get 1. So maybe I'll be precise and I'll just say that. I'll just, yeah, this is not precise, but pedantic is what that is called. Just showing every little step. Oh, sorry. Okay. Part B. Well, you see 1 minus cosine of x over x. That's the limit law over here, and that's equal to 0. Okay. And so what you can do with this is you could split this into a product of two limits, because you can view this fraction as this function times this function, right? So we have a theta squared plus 7 times the limit theta goes to 0 of 1 minus cosine of theta over theta. And maybe I'll put parentheses around that. I don't want to go to the side. I want to go vertically. I want to write it like this. So this guy is equal to 0. Okay. And what I want to actually emphasize is just because this is equal to 0 and you're multiplying does not mean you can right away say that the whole thing is equal to 0. You actually do need to compute this guy, 7. Okay. Now 7 times 0 is clearly 0, so that is good. Now, why do we need to be careful about this? I'm preempting some topic that you will learn in the future called indeterminate forms. And the very strange thing is this quantity 0 times infinity. You will see this quantity show up maybe a month from now. 0 times infinity is not 0, is not infinity, is not undefined, does not exist. It is an indeterminate form, meaning it can take multiple values, and the precise value that it takes depends on the situation that we're talking about. It depends on what is that infinity, what is that 0. You need more detail, more information to be able to conclude, because there are instances when it can equal 1. There are instances it can equal 2, it can equal 7, any number you want. Okay, you actually need more information, and you'll also see that some other indeterminate forms that show up, and there's like 4 other ones that I can't immediately recall. But so because of this 0 times infinity, you do kind of need to also figure out what is this other guy. Just because it's 0 times doesn't mean you can immediately conclude it's equal to 0. Just a thing to keep in the back of your mind when we get there a month from now. Okay, we have 15 minutes. I want to do 3 problems. Hopefully we can do it. All right. I have to find IVT now. Slides are so messy. Okay. Yeah, I think it's this one. Print screen. Okay. So now a little talk about IVT. So this is definitely something that people get confused about when they first encountering IVT. It looks very confusing, and that's okay. You kind of need to stare at it for a few hours to like get a sense of like what is actually going on. And you kind of need to think through it for yourself also. Like people will keep saying the same thing to you about what it is, but you only really understand it when you've actually sort of figured out it for yourself and like actually can talk yourself through it. Okay. But let me talk you through it. Let's see. So okay, the first important thing is that we must have that f is a continuous function. If f is not continuous, IVT does not apply, period. Okay. But if it's continuous and we have some interval, okay, then we can say some stuff about it. So in this picture, our interval is gonna be like here to here. So it's going to go from 0 to 5. That is our interval. And it's saying things about f of a and f of b. And that's sort of an interval off to the side here. So we've got an interval of 5 and 1 for the f of a and f of b. And really what this is allowing us to do is if the function is continuous and we know like that it travels from like 5 to 1, a continuous function that starts off at 5, ends up at 1, this is asserting that no matter what value in between 5 and 1, there's got to be some point, some time where the function hits that value. So for any time, say I wanted to find some point in time where the function hits this value m. Well, by IVT, I am guaranteed, and we can sort of draw it just by like, all you do is you go off to the side and then you go down and you find some time t or p in this case. So this gives us the fact that we have f of p is equal to m. So at the time p, f will take the value m. That's kind of the statement that we're trying to get to have happen. And IVT allows us this statement. Okay, so now let's go ahead and try to use it for these problems. So we want to show this function has a root in this interval. What I'm going to do, just for convenience, is I'm going to call this a name. We're going to call it f. And having a root, well, what does that mean mathematically? It means, and more precisely, having a root in this interval. So this is saying that we want to find f of p is equal to 0. So a root is a place where the function will give you back the value 0, where it crosses the the x-axis, right? Crossing the x-axis means that y is equal to 0, means that the function gives you back the value 0. So we want to find f of p is equal to 0 for some p inside the interval from 0 to pi over 2. Okay, and so I'm going to remark also, I'm using a symbol, a math symbol, very common for math people, I guess not so common for non-math people. This symbol means in. It also can mean element of, if you're used to things like set theory, element of, but in. So p is some value inside of this interval. All right. Right, so how do we proceed and use IVT? So the typical thing for IVT problems is that the actual interval given is what we use to find what we're trying to conclude. So let's just try to plug at 0 and at pi over 2. Okay, so at 0 we have 2 times cosine of 0 minus sine of 0. Well, cosine of 0 is 1, so we have 2, minus 0, so we get the value 2. Okay. And for the other equation, cosine of pi over 2 minus sine of pi over 2. Cosine of pi over 2, let me think, pi over 2. So it's going to be 0. And then sine of pi over 2 is going to be 1. So we get 0 minus 1, which is minus -1. Okay. So how does this help us? Well, over here, we first need like this interval for the y-axis. And what we can then say is that any point in the y-axis or in this interval we can guarantee there is some point in the x-axis that will give us back that output. And notice, so this -1 and this 2 are effectively these two endpoints there. And well, notice that 0 is inside. We want 0. 0 is the value we're looking for here. So this is all that we need to do this problem, actually. So I'm going to start writing the precise statement here. Since f of x is a continuous function, IVT applies. Since 0 is in the interval from -1 to 2, right? That's what we're sort of after with these calculations here. Since 0 is inside this, by IVT, there is some p, and then what it does is it uses the x values. Okay, so there is some p in. It uses parentheses. I've been using brackets. There's like a technical difference. I don't think it matters. There is some p in that, such that I'm going to use a math abbreviation. S dot T dot means such that. F of p is equal to 0, and hence p is a root. So this argument is very formal and math rigorous, and sounds very proofy, and that's sort of how these problems work out. So it will probably take a while of staring at this to sort of understand like what exactly is happening logically, and that's fine. Like this is just kind of the thing you have to go through to get used to this kind of argument. Let's continue and do number 6 and then 7. Okay, I think time should be fine. So for 6, we want to show that this equation has a solution in this interval. Okay, and it's also noting that this occurs precisely when this is equal to 0. Now this ties into the previous problem, because what we did for the previous problem was we found when is it equal to 0. Well, this is just another function. Okay. So the trick for this guy is kind of thing where like hopefully you've actually were like thinking about how to solve this before you came to class, because otherwise I'm sort of like spoiling the solution for you. Let h of x equal the difference of the two functions. Okay. And what does that mean exactly? Well, that means that we have h of x be 5x squared minus e to the x. Okay. And then we do the same kind of assumption where we like assume that the problem is given to us in such a way that like these are the actual values that we will be using to construct our answer. Okay, so we try testing, we try plugging at the endpoints. Okay, well, what is h of 0 going to be? So I have 0 minus e to the 0, which is going to be minus 1. And what happens if I plug in 1? I'm going to get 5 minus e to the 1, but e to the 1 is just e. So, okay, well, the key thing about this quantity is actually that it is positive. Right. Like before, we had a positive quantity and a negative quantity, and that was like that's what we needed because we wanted to guarantee that 0 was inside of that interval. So to guarantee that 0 is inside the interval, we just need a positive number and a negative number, and 0 will obviously be sandwiched between the two. How do we know this? Just in case you don't know, hopefully you would know, but E is approximately, these are supposed to be squiggly, E is approximately 2.718. Okay, just like you should know what pi is approximately. I guess we kind of think, oh, you should probably know what E is approximately. It's approximately 2.7. So this is a positive number. Okay. Right, now we can start to write our proof. So first of all, yeah, H is continuous. So IVT applies to this situation. And so then by IVT, I kind of want to rephrase this. So let me see. Since that is equal to that by IVT, there's something. Yeah. Okay. So yeah, since I'll just phrase it in the same way. So since 0, no. Yes. Since 0 is inside the interval from -1 to 5 minus e, doesn't matter what that is. That's just a positive number. By IVT, there is some p and then this case, p is a number on the x-axis, right? This argument is on the y-axis. This one is on the x-axis. So p is in the interval 0 to 1, such that, okay, now I'm sort of running out of space. So h of p is equal to 0. And to connect this back to the original statement of the question, what does h of p equals 0 have anything to do with that? Well, let's unpack what h is. H is f of x minus g of x. So this is saying, this is an implies arrow. So it's the fat arrow. It says implies that f of p minus g of p equals 0. And this is going to imply that f of p is equal to g of p. I kind of want to say something on the end of this. Yeah, okay, yeah. So I want to kind of repeat this part for some p in 0 to 1. And this is just to connect it back to the precise statement that you're being asked for. You want to show this statement holds true. Well, I have just done that. Right there. Okay. It was originally over here. So there's like that right there. So I just like repeated that over on this end. Okay. So I'm going to go a little bit over time just to make sure that I cover this part. So you're given some data, and the way to sort of represent this data to make sense of it is probably through drawing a table. So you have time values and you've got velocity values. And so at 1 p.m. you're going 60 miles per hour, 2 p.m. going 70 miles per hour. You could probably say mph. Fine. Argue why your speedometer must have read 65 at some point between these between 1 p.m. and 2 p.m. So this is also just IVT. You have the key assumption that velocity is a continuous function. So we're just going to assert that since velocity is a continuous function, IVT applies. And since 65 is a number between 60 and 70, right? Notice that in this picture, like we've got t here, we've got v of t here, you've got your 70 here, you've got your 60 here, you've got your 1 here, you've got your 2 there. This is the window that like corresponds to, I hope I can scroll, that corresponds to like this diagram. So like this is kind of the picture that you would have in mind. And so 65 is between 60 and 70. IVT guarantees there is some time t in the interval 1 to 2, meaning from between 1 p.m. and 2 p.m., such that v of that value t, that special number t, is going to be 65. And I guess I can put units mph. Yeah. So this is the math argument. It's all by intermediate value theorem. Okay. Well, that's all I want to go over for today. Are there any questions? So if not, then I'll see you guys next time.
Thank you.